Hello. Welcome to today's lesson on the life stages of stars larger than our Sun. In this lesson, we will describe the life cycle of stars larger than our Sun, including their evolution from a nebula to a red supergiant, the dramatic supernova explosion, and the possible outcomes for the remaining core, such as the formation of neutron stars or black holes. So far, you are familiar with the life stages of a star the same size as our Sun. You understand the processes that lead a star like our Sun to evolve through its life cycle, including becoming a red giant and eventually forming a white dwarf. Building on this foundation, we will now explore the more dramatic and complex life stages of stars much larger than our Sun. This concept will advance our understanding of physics by showing how these massive stars impact the universe, contributing heavy elements and extreme objects like neutron stars and black holes. Let's get started! Stars larger than the Sun start their life much like any other star. A vast cloud of gas and dust called a nebula collapses under gravity, forming a protostar. Then, when nuclear fusion initiates in the core, the star enters the main sequence, where it spends the majority of its life, similar to stars like our Sun, but on a much grander scale. Once the star uses all of the hydrogen in its core, it expands and cools to become a red supergiant. This stage is similar to the transformation of stars similar to our Sun into red giants, but the red supergiant is much bigger and brighter. For example, the red supergiant Betelgeuse has a radius about 1,000 times greater than that of the Sun. When a red supergiant star exhausts its nuclear fuel, it marks the beginning of a truly spectacular event. Throughout its life, the star has been fusing lighter elements like hydrogen and helium in its core, producing energy and maintaining stability. However, as the star ages and runs out of lighter elements to fuse, it begins burning heavier elements like carbon, oxygen, and silicon. Eventually, the star reaches a point where no more fusion can occur, as iron forms in the core. Iron cannot undergo fusion to produce energy, and this leads to a critical moment where the star can no longer support itself against the force of gravity. Without the energy from nuclear fusion to counteract gravity, the core of the red supergiant collapses in on itself, creating immense pressure and heat. This rapid collapse triggers an extraordinary chain reaction, where the outer layers of the star are violently ejected in a massive explosion known as a supernova. The energy released during a supernova is so intense that the star can outshine entire galaxies for a brief period. Not only is this explosion visually dramatic, but it also has a crucial role in the universe. The supernova disperses heavy elements such as gold, silver, and uranium into space. These elements are essential building blocks for planets, moons, and even life itself. In fact, the very materials that make up Earth and all living things were forged in the cores of ancient stars and spread through the universe by supernova explosions. After the supernova, what happens next depends on the mass of the residual core. If the core's remaining mass is between 1.4 and 3 times that of the Sun, it compresses further to become a neutron star. This object is incredibly dense, with a mass similar to the Sun, but only about 20 kilometers in diameter. The matter inside a neutron star is in an exotic state, primarily composed of neutrons. Due to their immense density, a neutron star's gravitational force is incredibly strong. If you could somehow take a sugar cube-sized amount of neutron star material, it would weigh billions of tons. Neutron stars also often rotate at incredible speeds, emitting beams of radiation that we observe as pulsars. However, if the core's mass exceeds 3 times that of the Sun, it collapses into a black hole. A black hole represents a point in space where gravity is so intense that nothing, not even light, can escape its pull. The boundary surrounding a black hole is called the event horizon, beyond which nothing can return. The formation of black holes marks the end of the life cycle of most massive stars. Black holes can continue to grow by accreting matter from their surroundings and, in some cases, can merge with other black holes to form even larger ones. By understanding the life cycle of massive stars, we gain insight into the dynamic and interconnected nature of our universe. These stellar remnants play a crucial role in the cosmic cycle, contributing the building blocks necessary for planets, galaxies, and potentially life. In today's lesson, we delved into the fascinating life cycle of stars larger than our Sun. We learnt that these massive stars begin similarly to smaller stars, but follow a much grander and more dramatic evolutionary path. We saw how, after exhausting their hydrogen fuel, these stars expand into red supergiants with impressive sizes, and how, when the nuclear fuel in a red supergiant is eventually depleted, it undergoes a supernova explosion, dispersing heavy elements into space. We then examined the fate of the remaining core, which can condense into a neutron star if it is between 1.4 and 3 times the mass of the Sun, or collapse into a black hole if it exceeds 3 times the Sun's mass. We also learnt that neutron stars are incredibly dense, while black holes represent regions where gravity is so powerful that nothing can escape. Finally, we touched on the fact that black holes can continue to grow by accreting matters from their surroundings, and can even merge with other black holes. By studying these stages, we gain insights into the dynamic processes that shape our universe and contribute to its complexity. Watch the rest of the GCSE physics course at Sophos Education.